In the last 10 or so videos, we've delved into different aspects of a transformer neural network, building one from theory and also code completely from scratch. In this video, though, I want to take this transformer neural network architecture and actually explain every single component from end to end. And to do that, I wrote out and blew up this entire architecture that looks kind of like this. And I know this might look a little confusing now, but as I explain it, hopefully we will understand why every single component exists and how it actually works in practice. And I'll be explaining a lot of concepts on the way, so let's get to it. On reading the Attention is All You Need paper, which introduced the transformer architecture, it doesn't seem like it was written with the intent to be the foundation of BERT, GPT, or language models moving forward. It kind of reads like a paper that less focuses on the architecture and more on accomplishing the specific task of language translation. And so we're going to also blow up and explain the same architecture using language translation from a language called English, which I'm assuming we all know, I guess. Maybe no judgment if you don't. And then to a language called Kannada, which I'm assuming you don't know because it's a very small South Indian language spoken in a very specific state, in a very specific country in the world. But I'm from that region, so I thought I would just create a translator to do so. If you want to code this out, do check out the Transformers from Scratch playlist. They are on the channel. Let's now talk about the high level of the transformer architecture. The transformer architecture consists of two parts, an encoder and a decoder. During training, the encoder will take the English words of the sentence simultaneously, and it will generate word vectors simultaneously. These word vectors are going to be eventually context aware, as we will continue to train the transformer. And this is because of the attention mechanism, which we'll get to shortly. To the decoder, we're going to take care of our Kannada words simultaneously, but we'll also pass in a start token to indicate the start of the sentence and the end token to indicate the end of a sentence. We will also pass in the English vectors that were generated from the encoder. For the labeled output of the decoder, we shift the translation to the left. This is because, given the start token, we want to predict the first word of the sentence. Given the start token and the first word of the sentence, we want to predict the second word of the sentence. And in case you don't know where this is going, if we're given the start token and the first two words of the sentence, we want to predict the third word, and so on. To determine the model's loss, we compared the prediction made with the softmax and the labeled sentence here. A common loss function used for this kind of problem is the cross-entropy loss. We would compute the cross-entropy loss for every predicted word, add this up to get a single loss. This loss is then backpropagated through the network to update the network's parameters. Now, during inference, let's say that we want to translate the English sentence, "How are you?" to Kannada. We don't have any contextual words, but we do have the English words. So we can generate the English word vectors from the encoder, but we only pass the start token of the Kannada translation to the input of the decoder. This will produce the first word in Kannada translation, which is Nivu. That's how you read this. We then take the start token and Nivu to generate the next word of the sentence, which is Hegididi. We now pass in all of these words generated and continue generating words until we hit the end token, and this will complete the translation. Now that we took a look at how training and translation inference happen at a very high level, let's blow this architecture up and look at some details. Before starting this out, let's lay out some hyperparameters that we're going to be using through the conversation. So we're translating from English to Kannada. We'll assume that the batch size is 30. The batch size means that we are passing in 30 sentences at once through the network in order to update the weights of the entire network once. And we have the maximum number of words that a sentence can possibly have is 50. And this applies to both languages to keep it simple and consistent when we're seeing in the diagram. I mentioned we have a batch size of 30, but why are we batching? This is for faster training. When training neural networks with gradient descent, we pass a single input, generate an output prediction, compare the prediction and the label, and quantify this as a loss. This loss is backpropagated to update the parameters of the network. And so for every training example passed into the network, the parameters are updated. This is fine for small networks since the updates are quick enough, but for networks like ours, which have like millions of parameters, the updates can be pretty slow. So instead of updating the weights after every single sentence, we will update the weights after seeing a batch of sentence examples. And hence, mini batch gradient descent is of common practice. And in our specific example, we are passing in 30 sentences at a time through the network before any update to our model weights happens. Now, why are we choosing 50 though for the maximum number of words in a sentence? This is so we have a consistent shape of tensors that pass through the model at any given time. There are many implementations too that dynamically size the input, but we'll stick with the same sequence length for every single sentence implementation for this video. Now let's come back to the encoder. So this is the start of the encoder where we have every single word over here. However, computers do not understand words, they understand vectors and numbers. And so we'll be converting each of these words into an embedding. Specifically, embeddings are vectors, and they are like 512 dimensional vectors in our case. So this cube structure over here is essentially a huge tensor that is going to be 30 cross 50 cross 512. That's 30 for this batch dimension, 50 for the number of words in the sentence, cross 512 for each single word representation. We then add a positional encoding of the same shape. These positional encodings are generated from sine and cosine functions, and so they consist of numbers between -1 and +1. They exist because the encoder takes in words simultaneously, but the ordering of these words actually matters. We have the first word followed by the second word, followed by the third word, and so on. This ordering, or positional encoding, is defined by a positional encoder. In the main paper, they are not learnable parameters, but they can be configured to be learnable parameters if need be. There is no evidence at the time of making this video to suggest that using learnable parameters is better than just using the sine and cosine functions to generate positional embeddings. I have more information on this in another video on positional encodings with code. We then get this final tensor over here that we pass through a feed-forward network in order to get query vectors, key vectors, and value vectors. So every word is split up into 3 vectors: a query vector, a key vector, and a value vector. In past videos on this topic, I have discussed a very specific differences between them, but this is honestly just for our understanding, and the difference isn't very explicit to the model itself. I've received a number of comments that dig a little too deep into the exact definitions of these 3 query, key, and value vectors, and we could construct some difference between them, but in practice, they could quite literally be the exact same vectors for the encoder case. And this is best represented with the encoder architecture, as the query, key, and values are merely the result of a feed-forward transformation, and they're really nothing special. Now, what makes the query, key, and value vectors different are the operations that we will eventually perform on them. Since every word is represented by 3 vectors, so we have every 512 dimensional vector converted into a 512 dimensions times 3, which is 1,536. So every single one of these 1,536 dimensional vectors now constitutes a word. And the reason we break this up is to perform the multi-head attention. Zooming out a little bit over here, you'll see that there's this huge white stacked block. So there's going to be 8 of these stacked blocks on top of each other, and I do that for 8 heads in this multi-head attention. This is masked multi-head self-attention. It is self-attention because we're trying to analyze the context and build context within the same sentence. So every word in the sentence is compared to every word in the same sentence, hence self-attention. It's multi-head because we have 8 of these layers. And then it's masked because we're going to be discussing the padding mask over here, since there are many sentences that are not 50 words in length, and so we would be adding padding tokens. But these padding tokens should not be considered when computing a loss and also performing backpropagation. And so we want to effectively mask these out. The logic you see in this one grid is just for one attention head. And like this, you can imagine that there are 8 parallel processes going on. So this 1536 dimensional word vector for every single word is going to be broken up into 8 pieces. So we have this query part, which is going to be broken up into 8 pieces, the key part broken up into 8 pieces, and the value part broken up into 8 pieces. Each piece is essentially going to be a 64-dimensional vector if you do the math. So that's 64 dimension of the query, 64 dimension of the key, 64 dimension of the value, and we stack them kind of in this way to get 64 times 3, which is a 192-dimensional vector representing every word for one head. What we do is take the query vector and the key vectors, and we will multiply them, and using these shapes, of course, that's 30 cross 50 cross 64, and 30 cross 64 cross 50. And if you do a matrix multiplication, this will be a 30 cross 50 cross 50. Specifically, we're doing the multiplication along these last 2 dimensions and not the batch dimension. The fact that we're comparing every word in the English sentence, which is the query vector, with every word in the same English sentence, which is the key vector, makes this a self-attention. This is the semblance of a first attention matrix. And typically after this, even before we add the padding mask, we might even do some sort of scaling so that we prevent all of these values here from the multiplication from exploding too much to high numbers or very low numbers, and thus also stabilize the training. Scaling simply means dividing every value in our self-attention tensor by a constant value. And the value that is used in the main paper is the square root of the key dimension size vector for one head. And since our key is 64 dimensions for one head, we would typically divide each value by 8 to scale. This will ensure the activation values are neither too large nor too small. But once we do that scaling too, we're going to add a padding mask. A padding mask will prevent the padding tokens from propagating values. Technically, they should be 0 for pass-through and negative infinity for masking. This is because we will eventually perform a softmax. The softmax operation uses exponents. So the exponent of 0 becomes 1, which is a pass-through, and the exponent of negative infinity becomes 0, which will mask or will block information from passing through. In practice, the way that we would accomplish this is for every single padding value, we would introduce a very low negative number, kind of like negative 10 to the power of 9. It can't be negative infinity because a future softmax operation might fail, because if every single row is going to be a negative infinity and we apply a softmax, you'll get 0 by 0, which leads to numerical instability. And hence, what we would do instead is apply a very low negative number so that there's going to be at least some form of pass-through that occurs even after doing all the math. But this pass-through is so negligible that it shouldn't really affect your training too much. So once we apply the padding mask, we will now apply a softmax activation, and then we will actually have an attention matrix. And in this attention matrix, you'll see that it's 30 cross number of words cross number of words. Number of words cross number of words. And so you'll see like a probability distribution for every single row over here. And so each value in this matrix is going to quantify how much attention each word should pay to every other word. We then apply the value matrix that we computed way back in the beginning over here in order to get a 30 cross 50 cross 64 dimensional value tensors. And these value tensors will be very contextually aware. And this is the output of just one attention head. But recall that we have 8 of these attention heads. And so if we concatenate them one after the other, we're going to get 64 times 8 of these, which is 512. And so this concatenated tensor is now a very much so contextually aware tensor, at least compared to the input to this entire multi-head attention unit. You'll see here now that we're adding a residual tensor. When performing backpropagation, the loss value propagates in the backward direction to change the weights. You'll notice the largest changes happen towards the end of the network since it's closest to the lost signal. But as propagation goes on in the backward direction, the change in parameters will continue to get smaller. This is okay for shallower networks, but as networks get very deep, we might run into situations where the loss might not be able to propagate to all parts of the network. And so the parameters don't change as the gradients vanish and no learning happens. Skip connections or residual connections help by enabling better propagation of the inputs in the forward direction and the loss in the backward direction. We see this a lot in research involving deep convolutional neural networks, and they're used here too. So once we add a residual tensor, we'll now get this new tensor that hopefully will carry out the activations and the weights and also make sure that these weights update. We then perform layer normalization. The goal of normalization is to ensure stable training, so activations during the forward phase and the gradient updates during the backpropagation phase are not too large in magnitude. Mathematically, normalization would involve subtracting the values with the mean and dividing by a standard deviation. In batch normalization, we normalize the values across the batch, that is the 30 dimension. But in layer normalization, we normalize the values across the feature layer, that is the 512 dimension. And so, for layer normalization, we subtract each value of the tensor with the layer mean and divide it by the layer standard deviation. Now, in practice, we add a very small epsilon term to the standard deviation, which is of the order 10 to the negative 5, in order to prevent a 0 divided by 0 case from occurring. Additionally, we also optionally use learnable parameters called gamma and beta to track changes across different training examples. I've explained the process with more details with examples and code in a video on just layer normalization too. We now take the output tensor, pass it through a feed-forward layer, and then pass it back through a feed-forward layer just to capture some more information. And then we'll perform the same addition of the residual tensor and layer normalization in order to finally get a set of, for every single word, we will have 512 dimensional tensors, and each of these tensors is going to be very well contextually aware. And this here is the output of the entire encoder architecture. Now, once we have very contextually aware items here, we're going to pass it through a feed-forward network, but I'll explain exactly what and why we have key and value vectors here. But before I do this, let's go back to the decoder architecture and explore the beginning of it. So with the decoder, we want to generate the output translation. And for this, we will pass in the input sentences with a start token, followed by the sentence values, followed by the end token, and then a bunch of padding tokens until we hit 50 words. Now, in much the same way as before, we add a positional encoding. And once we add a positional encoding, we're going to pass it through a feed-forward network to get query key and value vectors and perform mass self-attention as we did in the English case. So it's mass multi-head self-attention here. So it's the same dimensions. We'll take the query key value, split it up into 8 different heads, multiply the query and the key tensor. We have an attention matrix essentially over here, which we will typically scale before adding a mask. However, in this case, we not only need to add a padding mask, but we also need to add a look ahead mask. So a look ahead mask will ensure that the decoder is not cheating, because during the generation phase, that is the inference phase when you want to actually just start translating sentences, we don't have access to future Kannada words, the future destination target language words. And so during training, we need to apply a mask to ensure that it does not look ahead of its current self. So that means that the third word in the sentence cannot look at the fourth word in order to see what it can attend to. And so it cannot derive any contextual information from that during the training phase. And so we will add the look ahead mask along with the padding mask. We then apply softmax to actually get attention values and probability distribution like values for every single word, how much it needs to pay attention to every other word in that sentence. And then multiplying it with this value matrix, we'll get some value tensors, which we concatenate across all of the 8 batches over here in order to get the final concatenated tensor. We'll then add a residual tensor so that we can ensure that information is going to propagate. We apply layer normalization, and now we are going to get this batch over here, which I'll just call it directly as Q. This is going to be a set of query vectors that we're going to be inputting to our mass multi-head cross attention layer now. So in order to perform cross attention, this is going to be, instead of like every word in the sentence to every word in the same sentence, it'll be every word in this target sentence Kannada to every source word in the English sentence. And so the query represents essentially what am I looking for, and that's kind of what we would want to output. That's why this will be the query. The Kannada words will be the query tensors. And now, if you can see that there's an arrow that's coming in, but it's coming in from the encoder piece, which is providing, well, we saw these concatenated tensors that are very high quality. We're just going to put a feed-forward network of 512. It'll map 512 dimensions to 1024 dimensions. And so every one of these is for every word will be 512 and 512 for the key and value tensors. This will add English information that we have encoded into the Kannada vectors so that when we're generating the Kannada vectors, we generate an appropriate Kannada translation based on what the English translation has to say, or the English sentence has to say. So we have the query from the Kannada sentence, and then we have the key and value vectors from the English sentence, and then we perform multi-head cross attention, which kind of looks like the other self-attention case, but it's clearly the source of the query is different, and the key and values are different as well. So we'll multiply the query and key, get an attention matrix, which we will scale, as I mentioned before, to help numerical stability. In this case, we only need a padding mask. This is because every single Kannada word is allowed to see the entire English word sentence. Because we are, during translation phase, we have everything in the encoder. We have all of the English words already, since we need to translate it. And so we just need to add a padding mask just to zero out any padding information from excess tokens. We'll then perform a softmax to get a probability distribution values of how much attention should each Kannada word pay to an English context. And then we'll eventually get the similar value tensors, which we concatenate across the 8 heads. And this will lead to a 512 dimensional vector for every single Kannada word. And in this case, every Kannada word will have some English context now embedded in it as information. We'll add a residual tensor to ensure that we have extra propagated information throughout the network, because it's a very deep network. And then after performing some layer normalization for stabilizing the values and gradients and a feed-forward layer, we will end up with a 512 dimensional vector that is very context-aware. This entire decoder layer and also the encoder layer can be repeated. I put like a times n up here and also a times n over here. So essentially, after getting these tensors, we can actually create this entire architecture. It'll basically, the control will basically pass back here. And it has the same tensor shape. So we can basically perform this decoding phase again and again as many times as we need. Typically, it's done like a few times. Even once is fine, but it depends on your problem, depends on how many patterns are required to actually understand this translation. But essentially, once you have your final vectors, that is your final Kannada vectors that have English context embedded with them, you can take it into a feed-forward layer in order to expand it to the Kannada vocabulary size. Note the Kannada vocabulary is the number of possible words that our model can see and predict. In this architecture, we made it predict words. So the dictionary might be large and of the order of tens of thousands. However, the sentence sizes are small. You'll see the English sentence, "How are you?" is just size 3, and the Kannada translation for this is just of size 2. And many implementations use character tokenizations or even byte pair encodings to get a good balance of vocabulary size and maximum sequence length. So in this case, for every single batch, for every single word, we are going to have a vector that is the size of the Kannada dictionary. And this is so that we can make it interpretable to us humans. So once we apply a softmax on it, we'll get a probability distribution across all Kannada words, and we can just take the most probable word that it's supposed to be as like the prediction. And this is going to be compared to the labels. This here is the label, which is what it should be, what every single line. So the first line should be encoded as this first word, which is nivu. And the second line over here should be encoded as the second word, which is called heigidiri. And this third line should be encoded as the end token to represent the end of sentence. And it's based on these three tokens, the first three ones, that we'll be computing a cross-entropy loss, and then we'll be backpropagating throughout the network. And when I say throughout the network, we're basically going to be backpropagating through the encoder and decoder as well, because the encoder also has a connection over here. So all of the weights of the entire network will be updated once it sees one batch of 30 sentences. And so that's the entire transformer neural network architecture, and I hope you kind of got the entire context here. We can go through the inference part too. So the English sentence is passed through the encoder as we would during training to generate the context-aware vectors. To the decoder, we pass the start token followed by the padding tokens, and we ensure the padding tokens are all masked in the multi-head self-attention and the multi-head cross-attention. We'll get a probability distribution for the next words, but we just need the first row's probability distribution in order to just get the next word. From this probability list, we can take the first word corresponding to the largest probability, or even perform some form of sampling to generate the next word. And fun fact, the ChatGPT model makes use of this sampling technique, so the same words aren't always generated in verbatim. It adds a more human element or aspect to it. Once the first word of the Kannada translation is generated, we pass this word along with the previous start token as input. We update the paddings and mask for the self-attention and cross-attention components, and generate the second word. And we repeat this process until the end token is generated to get the complete Kannada translation. For more details, I have an entire playlist called Transformers from Scratch, where I'm building out different components of the transformer neural network and explaining concepts along the way in both theory and in code. So please do check it out. And if you think I deserve it, please do give this video a like. Thank you all so much for watching, and I will see you with another video very soon. Bye-bye.